we saw that this ferromagnetic state is actually part of a larger quantum phase of matter that's non-trivial, that's stable, with the important caveat that we impose this Ising symmetry, right? And so the goal today will be to present a quite different and more interesting phase of matter called the topologically ordered phase of matter. And this will also constitute another non-trivial and stable phase of matter, but this time we won't even need to impose any symmetry. Okay? There's no need to have this extra caveat. Okay? And furthermore, this topologically ordered system, as you'll see, it's much more interesting than transistor Ising model. There are pretty exotic particle-like excitations called anyons that can be neither bosons nor fermions. And if I have time at the end, I'll also mention how this topologically ordered phase is not only of fundamental interest, like there's these new particle-like excitations, but actually they might even be practical. We might be able to use them as what's called the quantum error-correcting code. So they might help us build a quantum computer that's robust to noise. Okay, so I'll be introducing topological order via one of the simplest examples of such a phase through a toric code model. Okay. Okay, so we'll go to 2 dimensions now. So the transistor Ising model I defined on a 1D ring. Now we'll consider a square lattice in 2 dimensions, and let's put a qubit at each link of the square lattice. Okay, so every dot here denotes a qubit, or spin 1/2 degree of freedom. And again, I want to consider periodic boundary conditions in both directions. And so I'll put this lattice on the surface of a torus. Okay, hence the name toric code. Okay, and the Hamiltonian for the toric code consists of 2 pieces. This sum over vertices of the square lattice of this A operator, and sum over plaquettes or squares of this B operator. Okay, so the A operator for a given vertex V consists of this 4-body ZZZZ interaction. Okay, and this B operator for every plaquette or for every square P also consists of a 4-body interaction, but now it's a product of Pauli x's. Okay, so we have these 2 different types of interaction in the Hamiltonian. Okay, so now let's try to again try to understand the physics of the ground state of this Hamiltonian. Okay, so one thing that we should first notice is that all these terms in the Hamiltonian they actually all commute with each other. Okay, so if you look at the A terms, that's a product of Z's. Z's always commute with each other, so A's commute with other A's. Z and X don't commute, but if you look at the product of these Z's and the product of the X's, then you'll see that they're either completely decoupled, they act on disjoint qubits, in which case they trivially commute because they act on disjoint qubits, or the more non-trivial case is when they intersect. So you can have a situation where you have a star here and a plaquette here, but then now you see that they only intersect at an even number of qubits, and so even though Z and X individually anti-commute, an even number of Z's will commute with an even number of X's. So even if these A and B operators have overlapping support, you can convince yourself that they'll always commute with each other. Okay. Okay, so that's important. A's, B's, all mutually commute. Okay, so we have a sum of a bunch of commuting operators, and so now it's somewhat easy to specify the ground state, right? So all these are, commuting products of Pauli operators. They all square to 1, and so we can find some state in which they all take definite value 1, right? So to minimize the energy of this Hamiltonian, I want all AV to be 1 and all BP to be 1. Okay, so this defines the ground state. Yeah. Which operators? These? Yeah. So sorry, maybe I should. Yeah, this is kind of pictorially defined. So AV is just a product of. So let's say this is like say Z1, Z2, Z3, Z4. Then AV is just defined as the product Z1, Z2, Z3, Z4. It's a product of 4 Z operators. That's what A is. Yeah, B. Yeah, so B is a product of. This is like X1, X2, X3, X4. Yeah, that's what I mean by this picture. Sorry, should have been more explicit. Yeah. What are multiples? Sorry, so V is short for vertex. Okay. So we have a sum over all vertices, and on each vertex, I have this 4-body operator coming out of that vertex. Yeah.
Maybe the question was, why isn't there a J multiplying this term, like the usual coupling manifold?
Why?
Normally we write sigma I, sigma J with the J multiplying it.
Oh, you mean like a coupling constant? Yeah. So here I've set the couplings to be 1 because we're not going to deal with any perturbations of this model. We're just going to deal with like if you want like a ideal model, kind of like the analog of the GHZ limit. Okay. Yeah. So these couplings are all just set to 1 by hand. Any other confusion? Okay. Okay, so the ground state is simply specified by just all these operators taking value 1, which sounds very simple in terms of operators, but we would like a better understanding of it in terms of wave functions as well, right? So, let's see what this means at the level of a wave function. So for any wave function, we can just expand it in any basis we want. So I can choose, say, okay, let me, okay, I'll stick with S here. So I can choose to work in the Z basis, let's say. So I expand my wave function in terms of configurations in the Z basis. Okay, and I have some amplitude associated with a configuration in the Z basis. And I apologize for the slightly different convention, but it's just easier to use in this case. So S at a given site, I'll label by 1 or -1. So this will be the usual spin up or spin down. So concretely, the Z operator acting on the 1 state is 1, and the Z operator acting on -1 state gets a minus sign. Okay? So, yeah, so I'm just expanding the wave function in terms of bit strings, 1s and -1s, and these are eigenstates of the Z operator. Okay? This is the most general form of a wave function. I haven't done anything, just saying I'm choosing to work in the Z basis. Okay, so now let's see what these two conditions mean. All the A's are 1, let's say for every V, and all the B's are 1. So let's first check this AV equals 1 for every V. So that means that at every vertex, I have some spin configuration, 1s and -1. So I have like S1, S2, S3, S4. And so what the product of Z being 1 means is that the product of all these numbers, which are plus or minus 1, should be 1. Okay? So that just means that there should be an even number of -1s. At every vertex, right? So just to be very explicit, some examples of this are if I have 1, 1, 1, 1, or I could have all -1, or I could have 1, 1, -1.
Why there can only be uneven numbers of -1?
Yeah, so I'm trying to understand what these operator constraints mean in terms of states, right? So these define the ground state, and for any state with AV equals 1, the product of these spins must be 1, must be 1, right? Yeah, so these are some example configurations that satisfy this constraint. Yeah. Yeah. I think I said that very, very briefly. So let me be more explicit. So AV squared equals BP squared equals identity. So the eigenvalues of AV and BP are all plus or minus 1. And they all commute, so we want to minimize the energy by setting them all to 1. Okay, so now it will be, again, convenient to represent things more graphically. So, yeah. Yeah, okay. Yeah, I think I see that. Yeah, I think it was a little bit too quicker. So, so we're interested in understanding the ground state psi 0, right? And psi 0 is defined by the conditions AV psi 0 equals psi 0, and BP psi 0 equals psi 0. Okay? So the ground state should be an eigenstate of all these operators, right? There exists one because they commute, so there's a simultaneous eigenstate, and we want it to be plus 1 to minimize the energy. Okay. Yeah, thanks. Yeah. Up to here, up to this point, we haven't chosen any basis. This is just a statement about operators, right? And so we just have to kind of inspect, right? If they're decoupled, if they act on disjoint sets, they definitely commute. The Hilbert space is a tensor product, right? But if they overlap, they always overlap in pairs, you can check. Yeah. So when they overlap in pairs, they commute with each other because you have two minus signs as you bring an operator past the other one. Yeah, okay, thanks. Right, okay. So it's useful to represent these ones and minus ones pictorially. So if I have a 1, sorry. Yeah, let me just maybe denote it here. So if I have a 1 state on the link, I will just not color it. But if I have a -1 state, I'll color that link green. Okay. So for example, this state will look like this, and then this state will look like this. Yellow I saved to have a different convention, but yeah, okay. Or maybe blue, maybe blues. Oh no, this is worse. Yeah. Anyways, the squiggle should be visible enough. So this squiggle means it's a -1 state in a spin configuration. Okay. So now we see that for every vertex, if the product, like for every vertex, if there are an even number of -1s, then the type of configurations that satisfy this A constraint are loop configurations, right? So I'm dealing with some configuration of 1s and -1s, and as long as my squiggles, or the locations of -1s, form loops, then this will always satisfy AV being 1 for every vertex, right? Because anytime I have a loop configuration of -1s, that's basically the definition of there being an even number of -1s, right? A loop is when you have something entering and something exiting a vertex, right? Okay, so we see that this A constraint, AV equals 1 for all the V, basically means that these spin configurations in my wave function must be loop configurations. Okay. So we're only allowed loop configurations for let me maybe more specific. So some general spin configuration must be a loop configuration for AS to be to have eigenvalue 1. Okay. Okay, so now we've kind of narrowed down our Hilbert space. Before we started out with the Hilbert space of all possible spin configurations, and to satisfy all the A's being 1, now we're only focusing on loop configurations, right? States with loops of -1s. Okay, so let's call these loop configurations. I'll denote them by like a ket C for configuration here. Okay, so we've learned a little bit more structure for the ground state. So now we see that psi must be a sum over loop configurations C with some amplitude for that loop configuration. Okay. So this is an example of a loop configuration. Are there any questions up to this point? Okay, great. Okay, so that's A. We basically, completely built in the A constraint. That's reduced Hilbert space to loops. So now we have to see what the B term is doing, right? So we want to make sure we want to find some state that's also an eigenstate for B's, right? So what is the B doing? Let's see. So again, we're only working in the Hilbert space of loop configurations. So let's see what it does on loop configurations. So BP, let's say for given P, acting on, let's say, the trivial configuration with no loops at all, BP is a product of X operators, right? So it'll just flip a bunch of spins from 1 to -1. It'll flip a plaquette from 1 to -1, right? So this will be, this will give us now a loop configuration here. This is at the location of P, the plaquette P, right? And then similarly, we can act with BP on a loop configuration like here. Let's say if it's acting on that plaquette at P, then it'll destroy that, right? It'll flip all the -1s to 1s, so we get back to our no loop configuration, right? And then similarly, you can see that if we have, let's say we act on a loop configuration here, but let's say that P is, let's say that it's acting, the operator BP is acting on a plaquette to the right of this loop configuration, then we'll get an enlarged loop configuration. Right, because the action of P is a bunch of X's here, and so it'll flip this spin back, but then it'll create 3 more here, right? So it'll enlarge this loop to this configuration. Okay, so BP is basically going from one loop configuration to another one, right? It's like enlarging loops, destroying loops, creating loops, right? And so so this means that in order to find a state that's the eigenstate of BP with eigenvalue 1, we want an equal weight superposition of all possible loop configurations, right? So again, the simplest example of this is, say you have just like a single Pauli X operator, right? And X flips spin up to spin down to spin up. So an eigenstate of X with eigenvalue 1 is just the superposition of up plus down, right? This is basically just slightly more involved, but it's the same idea. To be an eigenstate of this thing flipping between different configurations with eigenvalue 1, we want our ground state, psi naught, to be an equal weight superposition of all loop configurations. Okay, so again, C here denotes loop configurations. Let me put a asterisk here that I'll return to soon. Is this clear? Okay. Yeah, so here P is the plaquette to the right of this green one. And so I'm just illustrating that BP is a product of x's like here, right? So the x here will flip -1 back to 1, so that means we get rid of that link. And then, it makes these, right? So it just makes the loop bigger. Yeah. Okay, so now we have some more intuition for the ground state of this Hamiltonian. It's a massive superposition of all loop configurations. Okay, but we're not done, and that's because there are more important operators that are hiding that we haven't considered yet. Okay, so let's see. Okay, so first let's consider a non-local operator. Okay, let's consider a non-local operator that's a product of z's. A product of z's that wraps around, say, the horizontal cycle of this torus. Okay, so we have a product of z's going around one ring of the torus. Okay, and let's call this string operator Vx. Okay, and similarly, let's consider a product of z's that wraps around another cycle of the torus, say the vertical direction, and let's call this Vy. So these are non-local operators. These are supported on a whole string that goes around the whole system. Okay. So why are these operators important? Well, first, one can check that these operators, they commute with both A and B. Okay, so these operators are built out of Z operators, so they always commute with the A's because the A's are built out of Z's. And moreover, they also commute with the B's, right? The B's have X's, but you can see that they're defined as such that they always commute with an even number of X's. If you have a plaquette that's off the string, it trivially commutes. There's no overlap. If you choose a plaquette here, then it commutes because it anti-commutes with these two, right? Again, it always they always overlap in an even number of qubits, and so even though they individually anti-commute, together they commute. And similarly for Vy. Okay, so these non-local operators, they all commute with all AV, BP, and hence they commute with the Hamiltonian. Okay, so these are also conserved quantities that we must use to specify a particular state. Okay. So one thing you can also convince yourself of is that these operators are independent of the A's and B's we define. Okay? These A's and B's, if you multiply them together, you always have some support that's contractible. Okay? But here we have an operator supported on a non-contractible loop around the torus. Okay? So for now, just take it for my word that these Vx, Vy are independent of A and B. They cannot be obtained by taking a product of different A's and different B's. Okay, so this means that to fully specify a ground state, we must also specify the values of these conserved quantities, right? So these Vx, Vy, they commute with all the A's and B's, hence the Hamiltonian. That means to specify a ground state, we must also specify these Vx and Vy operators. And again, we see that Vx squares the identity, Vy squares the identity. And so Vx, Vy can take values plus or minus 1. Okay. So what we see from this is that we actually have 4 ground states. All right, so each ground state is not only defined by all the A's and B's taking value plus 1, that's the energetic constraint, but they should also be specified by these non-local operators taking value plus or minus 1. Yeah. Ah, okay, yes, very good question. So yeah, you're asking, okay, here, it's almost as if I arbitrarily chose a certain row to define Vx on, and you might think I've even more quantities by taking the next row, etc., right? However, this V operator can actually be deformed by using the A operator. So the A operator is like a star operator of Z's, right? And so you can see that if I, okay, maybe I'll just, maybe I'll just redraw this here. Yeah, so if I have this original Z operator, this string of Z's, but then if I now apply a bunch of star operators here, if I multiply Vx by a product of star operators, then all the adjacent ones cancel in pairs, right? Because they all hit twice. And then now this one also cancels the Z here, right? And so I end up with a product of Z's here. Okay, so the point here is that the Z operator on the next row is not independent of the Z operator here. They're related by a product of A's, because A's take value 1, right? And so you can combine them with operators as freely as you want. Okay. Yeah, it's a good question. Any other questions? Yeah.
Can you put these ground states in superposition, or it looks like some kind of selection rule?
Ah, okay. That's another good question. So here I've just if you want, I've kind of chosen a basis for this degeneracy, right? But indeed, all 4 of these states have the exact same energy. So I'm free to take any linear combination of these 4 states, and they'll all have the same lowest energy, right? Yeah, so this is just right now you can think of it as a basis choice for the ground state. The point here is just that there are 4 distinct ground states. Yeah. So let's get more intuition for what these Vx and Vy operators measure. Okay. So yeah. So let's go back to this wave function representation of the ground state. So here I already kind of swept some stuff under the rug. So here, let's say I build Psi0, by starting out with the trivial configuration with no loops. Okay, so I have no loops, then I start hitting it with all sorts of B's, right? I get 1 loop, I get a bigger loop, I get more loops, etc. Okay, so if I start from this reference configuration with no loops, then I'll build some wave function defined here. Okay, so which one of these which one of these states did I just construct? Okay, so let me be more explicit. So let's say psi0 was built from, let's say psi0 contains this configuration with no loops at all. Okay, let's say assume contains no loop configuration. So the question is, which of these ground states did I just construct? Any? Sorry? Yes. Yeah. Very good. So this state that I constructed, starting from the no loop configuration, has value Vx equals Vy equals +1. Okay? That's because I can first check this reference loop configuration that I started out with. Right? I started out with a configuration with no loops. That means everything is +1 there. Right? So I can just check that Vx is 1 for the all plus configuration, and Vy is also 1 for the all plus configuration. And then even when I hit this reference configuration with BPs, to generate loops on top of that, again, the BPs, they all commute. They all commute with Vx and Vy. So by applying BP, I cannot change the value of this Vx, Vy. So basically the short story is that Vx and Vy measures whether or not the winding of the loop, whether or not there are an even or an odd number of loops that are winding around cycles of the torus. Okay. So in this sample ground state that I constructed, there's even number of winding around the torus, like 0 or 2 or 4, etc. Okay. And then other sectors, when there's -1, for example, those are correspond to odd winding around the torus. Okay. So yeah, so just try to convince yourself what these other sectors mean. But the short story is that they measure how many the parity of the loops winding around each cycle of the torus. Yeah. Vx equals plus, and Vy is minus. Yeah, so if I start with, okay, yeah, I guess this is a good opportunity for illustration. So if I start with, a reference configuration that has, like a column of -1s, right? So this is one loop of -1s going around this direction. Then you'll see that now Vx takes value -1, right? Because when I cut like this, I'll pick up a -1, but then this one is still +1. Okay. Yeah, so this is the reference configuration, and now I can hit it with BPs to generate, sum over all loops. Yeah, if you don't have any loops going around, then no. So the example, the first example I started out with has no loops going around, no non-contractible loops. BP is going to start adding some contractible loops, but that cannot change the global winding, right? Yeah. Okay, so now we know that there are 4 degenerate ground states that are labeled by these non-local operators. And now let me just mention how we can go between these different ground states. Okay? So, so just as how we define these Vx, Vys, we can define similar operators for x's, right? So we can define a product of x's. It's like going around the horizontal direction. Let's call this Wx. And we can define product of x's going along a vertical direction. Call that Wy. Okay, and again, you can check that these operators also commute with all a's and b's and the Hamiltonian. Okay, and these operators can be used to move between these different basis states of the ground state. Okay, and the reason why this is so is because Wx, you can see, will anti-commute with Vy. Right? Wx is a product of x's here, and it'll hit Vy once. Okay, so so Wx, Vy will anti-commute, and similarly, Wy and Vx will anti-commute, which means that if you hit one sector, then now you can flip the value of the other conserved quantity. Okay. Maybe a more physical way of explaining this is just that these Wx, Wy, they just change the parity of the number of non-contractible loops, right? So remember, our canonical ground state here started from the no loop configuration, right? And then hitting it with BPs just adds loops, but the total winding number is even, right? But then if I hit this canonical example with Wx, then now I have an odd number of loops winding around the horizontal direction. Okay, so I'll be in a different sector now. Okay. Okay, so the summary here is just that I've labeled the 4 different ground states, and then I've shown you these operators which can toggle between the ground states. Yeah. Yes. Yes, and the reason is because Wx and Wy, they also commute with all the terms in the Hamiltonian. So if your original state satisfied all the Hamiltonian terms, then hitting it with W will also satisfy those Hamiltonian terms because they'll commute with the Hamiltonian terms, right? Well, again, this reference configuration is just one configuration in the full superposition, right? So again, the reference configuration is just to help you compute what the winding number is, because it's easiest to compute from that configuration. Once you have that, you must remember that you must add together all the other possible loop configurations, and then they'll satisfy the B terms. Yeah. Any other questions? Yeah. Yeah, so remember, the qubits are defined on the edges or the links of the square lattice. The qubits are at the edges. Yeah. The operators, A operators act on every 4 qubits around the vertex, and then B's act on 4 qubits around every plaquette.
So you don't actually have a qubit standing on the vertex?
No. The qubits are on the edges. Yeah. Okay, so I'm running a little bit short on time. Let me just say that we found non-local operators that can take you between the different 4 ground states. However, it turns out that no local operator can take you between 2 different ground states. Okay, and you can kind of already feel that in your bones in some sense because because these V's are measuring parity of winding number, right? And you can at least intuit that a local operator hitting a state cannot change a global winding number, right? So you need this type of non-local operator to move between the ground states. And this is one of the reasons why topological order, this model, is stable to local perturbations, right? If I now add some extra term to this toric Hamiltonian that consists of local operators, then again, it will be very hard to lift this 4-fold degeneracy, right? I will again need to go to some perturbation theory of order L to connect between the different 4 ground states, right? So this means that even if I perturb the Hamiltonian by some local perturbation, then these 4 ground states just split by an exponentially small in system size amount, okay? And notice that this argument doesn't rely on any symmetry at all. All it relies is on the locality of the perturbation, okay? So this toric code, these 4 toric code ground states are stable to arbitrary small local perturbation. Obviously, if I add a strong enough perturbation, eventually I can change to another phase. But yeah. Okay, so let me just in the last part, let me come to this slightly more exciting thing about the excitations of this model. Okay. Okay, so let me keep the Hamiltonian. Okay, so we've hopefully understood something about the ground states, this model. Now let's look at the low-lying excitations. Okay, so yeah.
These operators, so they look very bosonic, but they can both create and destroy groups. So is there some sense in which you can think of them as Majoran Fermat?
That's an interesting question. Well, not immediately. I mean, there is a way to understand this model in terms of Majorana fermions. That's true. But at least right now, I don't know if that follows from the intuition you stated here. Let's talk after. There is a way to represent this in terms of Marianas, if you are interested. But it's kind of orthogonal to, yeah. Okay, so we want to look at what are the excitations of this model. And yeah, so does anyone have any idea what the low-lying excitations are? So what are excitations? Like, so we look at the ground state where all these terms take value 1. Yeah, okay, so now I want some of these A's and B's to take the opposite value, right? Then there'll be higher energy, right? Okay, very good. So let's see what we can do. So let's hit a qubit here with an X operator. Okay, so sorry. Let me denote this picture by let me represent any of the 4 ground states. It actually will not matter which one I choose by this picture. Okay, so this in the back of your mind should be a fluctuating superposition of all loops. Okay. Okay, so for this state, all the A's and B's take value +1, right? That's how the ground state is defined. So okay, let's try creating an excitation. We can hit a qubit with an X operator here, and so the X operator, it does nothing to all the B's, because the B's are built out of X's, so the X's commute with each other. So the only thing that the X does is it violates the 2 A's on the stars nearby, right? So we have a star here made out of Z's, a star here made out of Z's, and the X will violate that now, right? Before it was +1 in the ground state, but then now, let me call this X1. Now, this X1 acting on the ground state will create 2 excitations at the endpoints, right? So this will be where AV equals -1, right? Okay. Okay, but now the point is that I can apply another X operator, say here. Okay, so now I can apply X2. And what does this do? That's right. So X2 will now remove this excitation, right? Because here AV was already -1, but then X2 will flip it back to +1, right? So then now I have an excitation here instead. Okay? So you can see that with a string of X operators, I can create these excitations at the endpoints. It's just how in the transistor Ising model, in the ferromagnetic phase, we applied a string of X operators to create a domain, right? And then we have domain wall excitations, right? So here the story is kind of similar. We can apply a string of X operators. Yeah, let me call this string of X operators UX tilde. Okay, so this string of X operators, it'll just create a pair of excitations at the endpoints. And I can make this string arbitrarily long, right? And it'll cost the same amount of energy. Only the endpoints will cost energy. Okay, so that's why it's, again, reasonable to think of these endpoints as deconfined particles. Okay, and they're called E particles in most literature. Okay. Okay, so the summary here is that I can use a string of X operator, this UX tilde operator. I can use it to hit the ground state, and then I create pairs of excitations at the endpoints. And I could do the same thing for the B's, right? So I can, for example, so I start with the ground state here, right? And then I can hit this ground state with Z operators. Okay, so if I hit it with a single Z, again, the Z's commute with all the A's, right? So the Z's don't create any A excitations, but this Z operator will create 2 B excitations here. Okay. Right. So the B here was a product of X's, and Z will anti-commute with that. So Z will flip that value of BP to the wrong value, right? And again, I can so this will be hitting the ground state with Z. Now I can hit the ground state with more Z's, and now this will basically hop this excitation over here. I can hit it with another Z, this will hop it over here. I can hit it with another Z, this will hop it over here. Okay, so I can consider similar strings of Z's. And now let me call these string operators UZ tilde. And as before, they'll create pairs of excitations at the endpoints. Okay. And these are called M particles. The reason is because E stands for electric, M stands for magnetic. Yeah, I can explain more the convention of that later, but right now I'm running pretty low on time. Okay, so these are the low-lying excitations of the toric code, these endpoints of strings. Okay. So now, now we want to understand these excitations a little better. So first, if we take 2 E particles and we move one around the other, okay, then nothing much happens, right? Because we move one around the other by using a string of X's, right? But the X's always commute with X's, so the E's are just bosonic with respect to each other. And similarly, the M particles are all bosonic with respect to each other. Okay, you can just move them. You can exchange them, and nothing happens. You don't pick up any sign or anything. However, something interesting happens when you move an E particle around an M particle. Okay. So let me again draw a square lattice. Okay, so let's start out with a state that I'll, sorry, yeah. Let me start out with a state that I'll label EM that's obtained by acting on the toric code ground state with some string operator X tilde and some string operator Z, UZ tilde. Okay, so pictorially, I want to consider having applied some string operator UX tilde to create a pair of E excitations here, and then the other partner is somewhere, let's say, far away. It doesn't really matter. Okay? And then I also want to have applied U tilde Z, again, connected to some other M particle somewhere far away. Okay, so I started out with the toric code ground state. I applied these long string operators to create pairs of E and pairs of M excitations. Okay, and their partners are far away. I don't draw them, but I'm just interested in the pair right here. Okay, so this is the definition of this EM state. It's an excited state of the toric code. Okay, and now I want to see what happens when I move around the E particle all the way around the Z particle. Okay, so I want to move this E particle all the way around this M particle. Okay? And I can do that by applying the same string operator, this UX type operator, right? So I want to move it around by applying this product of X operators. Okay? And so let me call this product of X operator 3, 2. Let me just be precise, call this product of X operator, let me just say this UX. Without this tilde. Okay, let's say the tilde denotes these string operators, and without the tilde is just this operator I use to move this around the other one. Okay, so let's see what happens to this excited state EM after I apply this movement operator. Okay, so so I have UX acting on EM, right? And that's basically acting on UX tilde, UZ tilde, toric code ground state. UX and UX tilde commute, right? They're all made out of X's, so I can bring it over. But then UX and UZ tilde, so UX and UZ tilde, now anti-commute, right? Because they intersect once right here. Right, so the X will anti-commute with the Z here. So that means that this equals UX tilde, UZ tilde, UX ground state, with a minus sign, right? Okay? And then finally, UX ground state is just a ground state, right? If I act with this operator on the ground state, it just does nothing, right? Because this is the same thing as creating like a pair of E excitations and then annihilating them. Or if you want, you can write this UX operator as a product of BP operators. Okay, you can write this UX operator as a product of a bunch of BP operators in the middle. Okay, so there are many ways to see this, but in any case, UX acts trivially on the ground state. So this is just the ground state. So you can see that at the end of the day, I just pick up a minus sign. Okay? So the summary here is that by moving an E particle all the way around an M particle, I actually get a non-trivial phase factor -1. So this E and M particles actually have non-trivial mutual statistics. Okay, they're not bosonic with respect to each other, right? Yeah, okay, I'm almost done. So it's useful to represent this in terms of a space-time picture, or at least what maybe a condensed matter would call a space-time picture, not the curved space that Pedro deals with. So one can represent this process of braiding by the following. So the M particle just stood still, right? M is yellow. So the M particle did nothing, and this E particle, I'm moving it around, right? So I have an E particle here. Okay, so the E particle, I move all the way around the M particle. Okay, let me just. Okay, and the derivation here says that this is just equal to a minus sign of the particle is just propagating trivially in time. Okay. So with this type of picture, now one can actually derive a lot more of this model, a lot more of the non-trivial properties of this model. So one other interesting thing to look at is the combination of E and M. Okay. So we can look at okay. So we can look at an E and an M pair. Okay, and let's see what type of particles these are. Okay, so we want to exchange a pair of E and M particles. Okay, one can create a pair of E and M particles nearby just by applying string operators that are near each other. Right, just take the two strings together. So here we're taking two E and M pairs. We're taking a pair of E and M's, and then we're exchanging them. And so, as I said before, E and E are bosons with respect to each other. There's no non-trivial statistics, so we can just resolve this crossing here. And then similarly, M's are also bosons with respect to each other, so we can just resolve this crossing here. But then now you see that the M and the E, that we're actually taking an E fully around the M as we did here. Okay, so this process between the M and the E incurs a minus sign. Right, so what this shows is that we get a minus sign relative to just the trivial propagation of these pairs. Okay, so what this means is that the EM pair is actually a fermion, right? So by exchanging these pairs of particles, we actually got a minus sign. See? So the EM composite is actually a fermion. So this is quite remarkable. You know, we started out with a model of qubits, of bosons, and yet, you know, through these, you know, a wise choice of interaction, we get particle-like excitations that actually have fermionic statistics. Okay. So I think I've used up a lot of time now. But yeah, I think this is really one of the most fascinating aspects of topological order. Many people in the world seriously believe that the fermions in our current world actually are emergent, right, from some completely bosonic model, right? And so who knows? Who knows? But in any case, I think anyone would agree that this type of phenomenon is quite fascinating, and people are trying to build this model in the labs for the purpose of quantum computing. And there's much more can be said, but I hope I've given you some flavor of this non-trivial phase of matter. So let me just take questions now.
Questions?
I don't know if this is like a valid question, but would you care to talk a little bit about the last part of the lecture, quantum code?
Yeah, okay, yeah, thanks for setting me up for that. It's always useful. Yeah, so for quantum code, like why is this a good quantum code? So the whole idea behind a quantum code is that you want to encode information into many degrees of freedom so that it's less susceptible to noise, right? So like say I want to do like some unitary gate on 2 qubits, right? If I'm doing that unitary gate on 2 physical qubits, like say 2 ions in my lab, then that's not so good because it's easy for some perturbation to flip that physical qubit around, mess it up, right? So the whole idea behind a quantum code is that now I want to, say for this 2 qubit example, I have a 4-dimensional Hilbert space, right? I want to realize that 4-dimensional Hilbert space not by 2 physical qubits, but say by a subspace of a huge Hilbert space. Okay, so in this particular case, I want to realize that 4-dimensional space by the ground state subspace of this Hamiltonian. Okay, so these 4 degenerate ground states we derived earlier. You can imagine trying to do a computation within that 4-dimensional manifold. Okay, so the reason why that's more robust is now it's harder for some perturbation to mess up that computation, right? So remember, I said that these 4 different ground states, they're not connected by any local operator, right? So like for this noisy setting, I said some excitation might flip a physical qubit and mess it up. But now flipping a qubit would mean going from one ground state to another ground state, right? Going like between these 4-dimensional states, you need to go between different ground states. But that's hard, right? So yeah, that hopefully gives you a little taste of how a quantum code should work. You're encoding information into a set of many-body wave functions that's harder for noise to corrupt.
So if you change the boundary conditions or the topology of the manifold you're putting in your system, does something dramatically
Yes, that's a good question. So indeed, I think I didn't even try to explain the origin of the word topological order. And I think there are many manifestations of topology throughout this model, but one important one is along the lines you suggested. So here we define it on a torus, right? Genus 1, right? But if you put it on a manifold with higher genus, you actually see that the ground state degeneracy changes. Okay? In fact, it grows exponentially with the genus of the manifold you put it on. So basically, to analyze those other cases, you would have to define more of these non-local operators that parameterize the ground state. And you would have to, do a dimension counting in your Hilbert space more carefully. But yeah, it does depend very sensitively on the topology of the manifold it's placed on, which is why, one of the reasons why it's called topological order. Yeah, this is unlike the symmetry breaking case, right? Like the transistor Ising model we considered. There, you just get ground state degeneracy 2, regardless of which manifold you put it on, right?
More questions? Yeah, okay. If not, let's thank Tim. And we are done with the lectures. So tomorrow we have the exam at 9:30. So do not stay until 4 a.m. studying for, or 5 a.m. There's no point in studying for tomorrow's exam.